Good afternoon, everybody. My name is Cano Diaz. I work in the Institute of Astronomy here in Mexico. Today I'm going to talk to you about the special recent star formation main sequence of galaxies. The study of galaxies and the study of evolution of galaxies is highly benefited by the use of large samples of galaxies, because one derivation of these studies is the statistical studies, and one result of the statistical studies is the derivation of scalar relations. One of the most well-known scalar relations in astronomy is the star formation main sequence of galaxies, which is a relation that relates the stellar mass and the star formation rates of the galaxies. The star formation main sequence relation has been shown to exist for several star formation indicators in several wavelengths and also at different redshifts. The general characteristics of this relation is that it's mostly linear, and it has a shape of that equation. It's a linear equation in which the values for the 0 point and the slope may vary considerably within the literature. However, the most recent studies try to constrain these values for both the 0 point and the slope for these small ranges. We can say that maybe these high variations in the regions of the values for the slope and the 0 point may come from observational bias. For example, many of the studies that study this star formation main sequence relation use a single fiber spectroscopy, which is a central fiber that is drawn there, for example, in the center of that galaxy, and which that spectroscopy is used in order to classify the origin of the ionization of the gas. Of course, if we use IFS technique, that will be highly benefited, because for obvious reasons we can have both spatial information plus spectroscopy. For this work, I used the Khalifa survey data. I used the B500 setup, and I selected a sample of galaxies to be low-inclined galaxies that fulfill this criteria of inclination lower than 60 degrees. For that reason, I was left with 306 galaxies from the Khalifa survey. I also need to say that my sample of galaxies within the Khalifa survey, it has a little bit more larger range of masses, because I used also the extended Khalifa sample, so I was able to have some galaxies that had lower stellar masses. I used the derivation of the stellar masses and the emission line flux maps was done with the Pipe 3D tool. Plus, afterwards, the star formation rates were derived with the H-alpha emission line through the Kennicott relation. I also need to say that this was not the first result that shows the star formation main sequence using the Khalifa data. There have been two previous works. One of them is the one of Catalina Torresilla 2015, who derived the star formation main sequence relation for integrated quantities, and also the work by Sanchez et al. 2013, who built this spatially resolved the star formation main sequence relation using only H2 individual regions of the galaxies. So first of all, we started trying to reduce the results of the literature, trying to build a star formation main sequence relation of integrated quantities for the galaxies, which is what I am showing in this plot. And then I also did some sort of classification scheme in order to make sure that the star formation main sequence relation, it was built only with the star forming galaxies. So for that purpose, we decided to use this scheme of classification. First of all, the galaxies that lie above the QD demarcation limit and had H-alpha equivalent widths larger than 6 angstroms were considered to be dominated by AGN activity. And those are the green points. There are only 4 points in that plot. Then the galaxies that lie below the QD demarcation limit and have H-alpha equivalent width larger than 6 were considered to be star forming in general. Those points are the blue points in the plot. Those points are indeed the star formation main sequence. Then the galaxies that had equivalent width of H alpha lower than 3, regardless of the position in the BPT diagram, are considered to be retired galaxies, because those are galaxies that whose ionization of the gas may be triggered by post-AGB stars, and those points are the red points in this plot. And this sequence, this red sequence, we call it the retired galaxy sequence. And those points that are left are those galaxies who had equivalent width of H alpha ranging between 3 and 6, and those are unclassified points and are the black points in this plot. The general characteristics of the star formation main sequence and the retired galaxy sequence, that is the red one, are shown here. As you can see, the slope and the 0 point of the star formation main sequence is in good agreement with the literature. Also, the scatter is quite low, which is also in concordance with the literature in general. We found 2.2 decks, which is very good in agreement. And from now on, I didn't study in more detail the retired galaxy sequence. Here is the main result, which is the special result star formation sequence for the Khalifa survey. And this plot is a density plot in which each point was selected to fulfill the same criteria that was shown here. That is the criteria for selecting the star-forming galaxies. That means that all of these points fulfill the criteria of having equivalent widths of H alpha larger than 6 angstroms and that lie below the QB demarcation limit. And regardless of the position of their host galaxies in the integrated plot. Actually, 11% of the points of this plot come from galaxies whose global ionization was not dominated by star formation. Here are the general characteristics of this spatially resolved star formation main sequence. As you can see, I didn't mention that. First of all, the colors of this plot are the color code is related to the number of points. So and also the contours are, I don't know if you can see them, but the contours show the 20, 40, 60, and 90% of the data. That means the total number of the points. So here are the general characteristics, that means the fitting of this relation using 100% of the data and 80% of the data. As you can see, the slope and 0 point is more or less similar to the integrated relation, and also the standard deviation or the scatter of this relation is quite small as in the integrated case. So just some conclusions. We found during the analysis of the integrated plot, we found two main sequences, the star formation main sequence and the retired galaxy sequence. And also we explored in further detail the counterpart of the star formation main sequence for the spatially resolved or the local case. And probably this local relation suggests that indeed the star formation processes are indeed local and are related and are strongly related to the gravitational potential. Of course, this is just the first step into investigating this issue. So what else can we ask ourselves in order to learn more? Well, first of all, we ask if this spatially resolved star formation main sequence has any dependence with any other galaxy properties like morphology or environment. We also haven't studied in any detail the spatially resolved counterpart of the retired galaxy sequence. Also, we would like to use larger samples in order to confirm our results. And of course, the next step will be to study this spatially resolved star formation main sequence for higher redshifts. So just one last slide is a work in progress, because I am trying to reproduce these results using the MANGA survey, because first of all, MANGA is a much larger survey. For example, just I built this spatially resolved star formation main sequence diagram using the MANGA results so far. I built a sample of also low-inclined galaxies fulfilling the same criteria of inclination, and I already got a sample of 923 galaxies. And of course, using a larger sample will be very useful in order to answer the questions that I addressed before. Thank you.
Okay, we have time for a couple of questions. If anyone wants to do. Okay, Vladimir. No? Okay. Now, Daniel.
So this is interesting to compare the two. Now the global star formation main sequence, there's a slight subtlety that the slope is not exactly 1, but slightly below that. So do you find that same for the local relationship, or is the slope 1 there?
No, actually the numbers are not exactly in agreement, but I think we really need to study further, especially to try to address these questions like, is there any dependence with other properties of the galaxies in order to see if that may help in order to do a better agreement with the slopes and the 0 points. Probably maybe that's something that we should study right now, especially with a larger sample like Manga 1.
But they are different, they are of one, they are not one.
They are not one.
No. Can you show the thing? So it's 0.72, the other one is 0.8.
Yes, it's flatter.
But far from one.
Mariana, in the case of the spatially resolved star formation rate, you didn't include the red eye or quasar galaxies.
No.
If you include them, they will follow a sequence or it will be a cloud. And
it's more of a cloud. Yes, actually, yes. This diagram, if we include the points coming from the retired galaxy, of the retired points, it has an S shape. It's more of a cloud than a sequence. Yes, that's why we want to study them differently or separately.
Because I think in the case of the global, you obtain a sequence, but this is by selection methods. So
yes.
Amazing. We have time for another question. Okay, sorry.
If the gas in retired galaxies is accepted by all stars, how do you measure the star formation rate?
The star formation rate is just using the chemical law that is just a derivation using the H-alpha line flux. So it doesn't mean that it's actually a star formation, it's just scaling the H-alpha line flux. That's why we are warning the readers of the audience that even if we are showing star formation rate, it may not necessarily mean that it's a star formation rate. It's just a linear transformation from the H-alpha line flux.
Okay, no more questions?